Hey, welcome back. So here we are. Previous part of this video, if you're on YouTube, showed how I solved all these problems relative to creating a flying wing design that is spin-proof. And I was very happy with all my solutions. I was thrilled that they were working. Things I learned along the way, very important, allowed me to create a design that I felt I could really move forward with and start building the full-size version, which I did. Moving ahead, I start building components. At the same time, I decided to go ahead and do more stability tests with this quarter scale model, of which I have the wing panel here. And quarter scale will give you a better feel for the dynamics of the vehicle, and the aerodynamics are a little more accurate also, so it's always a good idea. And so I'm building full-size components, and then I build this model, and I work into it all the solutions that I developed on the 8th scale models that we showed earlier. And I get it out and launch it, gliding along nice, flies good, doing some flying around, and I like how it handles, and yes, it has different inertia, and I like it even more. And then I start doing a bunch of maneuvers with it. And of course, key to those maneuvers is doing stall testing. And flying straight ahead, pull it up, oh, nice, gentle, straightforward stall, nose comes back down, we recover, as predicted. Well handled, easy to fly through the stall. And then I start doing slow turns, and darned if the thing doesn't break into a spin. I was like, oh my God, I thought I solved that problem. And I got everything like I had it on the 8th scale model. Why are the spins back? It's not an incredibly aggressive spin like it had been in the past. Obviously, some of the functions that I built into it are still working to prevent the spins, but it is decidedly not spin-proof. And at that point, a little bit of panic started to set in, because here I am building components for the full-scale aircraft, and the main problem that I was out to solve is back again. And I'm like, holy cow, what went wrong? And I racked my brain for a couple weeks and couldn't think of anything. Just kept building the full-size one. I said, so I'll build components that I know that if I need to change the design, I can work around it. And worst comes to worst, I can just placard the thing so that the CG's in a certain place and certain control throws, and just limit the maneuverability of the aircraft and limit its flight envelope to stay away from spins. That's a worst case solution to the whole thing. And kept thinking about what might be going wrong. Eventually, when I got up enough time and courage to go back and do more testing, I started doing some tough testing, looking at the flow conditions, and started running into some very interesting laminar separation bubbles. And I have a whole pile of very interesting video of toughs doing strange things when you least expect them to do those things. And worked through that, talked to friends. We ran through a list of all the things that might be happening, causing these strange flow conditions. Like, okay. Still had no solution to the problem. It's not like anybody went, aha, you did this and that happened and it now spins again. It's just nobody had any ideas, and a bunch of really smart people thinking about it. So I had to go back to engineering basics. And of course, a basic thing in engineering is, what did you change? What was the last change you made when you went from good to bad, or from bad to good? What is the one thing that you tweaked? What did you do a little bit different? And just get right down to the basics. What's the last thing you changed? Well, what was the last thing that I changed? Well, the early models had dihedral in the middle, and this had dihedral out at the tip. And I couldn't fathom how that might possibly be impacting the stall spin characteristics of the aircraft. The more I thought about it, no, the dihedral at the tip couldn't be it. Had to be something else. And so I started running down the list. What did I change? What did I change? Well, I changed the size of the elevons. It changed where the aerodynamic center of the elevon itself was located. It's now further inboard. and therefore a little bit further forward. Maybe that has something to do with it. And I had removed this flow guidance gap here. I had actually run the elevon all the way out to the winglet. And, oh yeah, that's right. All of a sudden dawned on me. I had changed the washout pattern in the wing. And if you go see the other video on aerodynamics of flying wings and aerodynamic analysis using X-foil, you'll see that I run through a bunch of options on washout and look at the different performance for the different configurations. These versions had 8 degrees of washout in them from here to the wingtip, linear. 0 degrees and then 8 degrees of washout at the wingtip. Straight twist. Both of these models, both the double taper and this one. That is not the most aerodynamically efficient configuration. That has a very much a bell-shaped lift distribution. It's nice and stable on yaw, but it doesn't give you the max L over D. And you can go see that other video and see how you do get a better L over D. You got to get closer to an elliptical lift distribution. And as I went closer to an elliptical lift distribution, I have to bump up the size of the winglet a little bit to improve the yaw stability that I'm giving up by changing the lift distribution. But I managed to push the predicted L over D up by 10%, 12%. It's a pretty good gain. And I didn't want to give it up. So what had I done? I had set up the center section of this wing, which for the model, actually I should go back over here, on the models was basically the center section of the wing goes out to where the elevon starts. On this model, it had been about here to here on the course. That center section of the wing, no washout. 0 to 0, straight wing. So, and then for here, I had a washout of 0 at the root end of this panel, which starts at the end of the flap and the beginning of the elevon, and 3 degrees here where the winglet is. And then from the 3 degrees here to 8 degrees at the tip. So the total washout in the wing, still 8 degrees. However, most of the washout is shoved out to the tip. That means the center section of the wing, the inner panels in the center section, are operating much more efficiently. If you could divide up a wing and say, I'm only looking at the efficiency factor of this portion of the wing, Oswald's efficiency factor is considerably higher because I've lowered CD0 by reducing the amount of twist in the wing. And the center section, even better. No washout at all. So a nonlinear washout, straight, gentle washout, and then a whole bunch out at the tip. Horton Brothers did this on their designs. There have been other flying wings that have been done that way, where it is a nonlinear washout in it, you get better performance. But what could that have to do with spins? And I, thinking about it, did more testing, fiddling around with it, changed the elevon, put this gap back in here, and helped straighten out the flow some. Well, it helped a little bit, but it didn't prevent the spins. And the more I thought about this, the more I thought about it. The elevon goes up, the elevon goes down, pushing the flow out along the tip. What is the difference between this elevon and this elevon? Oh, okay. The percentage of chord, the elevon chord, relative to the whole wing chord, is different between this configuration and this configuration. As a matter of fact, when I first finished this one, I did something very conventional. I made the chord of the elevon the same percentage of the wing chord all the way out. And that means that the elevon actually tapered, that the chord of the elevon was bigger here at the root than at the tip. So here I have elevons that are no taper, they're straight, or barn door elevons if you prefer. Previously, this one ran from here. You can see here, they were wider at the root, and then they tapered down as they went out. So I've made two changes. I've changed the washout, and I've changed the taper of the elevon. Why did I change the taper of the elevon? We know why I changed the washout. Why did I mess with the elevon shape? It's a little easier to build. If you're going to have a tapered wing, it's just an easier build to not have the elevon changing percentage of chord all the way out. Just keep the same percentage of chord all the way out. Pretty easy to build. Very typical configuration. You go look at tapered wings, they almost all have tapered ailerons or whatever control surface is on there. Another reason that you do it is on full-size aircraft, there's quite often a second spar. You have your main spar that's carrying your loads, have a second spar back here. That spar comes in really handy because you're going to mount a control surface on it. And it's easier to put in a spar and build the wing if it's running along a constant chord position, constant percentage of chord. It's just how wings are built. It's standard configuration. And having elevons that are a different shape, well, you'd have a spar running at a weird angle, you'd have these percentages changing, and it's not done as often. So basically, I designed it like you would any other aircraft. I just use standard design methodology. However, so different twist, different elevon shape. Okay, so I got two factors going on, and I don't know which one's driving it, but I changed two things at the same time. I know, big no-no. So I got to sort it out. The only way that I can sort out which one's causing the spins to show up again is to eliminate one of them and change the configuration back so there's only one change. And of course, it can't change the washout, just build another whole glider, but I can change the shape of the elevon. So what I did is I went back and I changed the elevon on this wing to match what had been on the original configuration. Change that. And what do you know? The strength of the spin and the aggressiveness of the entry and how easily it would enter the spin completely changed. Spins were still there, but much more benign, much easier to recover from, less scary, and much more predictable. I was like, holy smokers. And it wasn't a huge change. And it's not any significant change in elevon area. It's just a change in the planform shape. It's a change in what the elevon looks like when you look at it from the top. From a tapered elevon to no taper rectangular elevon. Now, how could that possibly be impacting spins? And yet, there you go. That's what was causing the problem. And I had to think about it for a while. And, you know, I wish I could recall what made the light bulb finally go on in my head, but I don't. It's like one of those things, you leave it in the back of your brain, you let your brain work on it while you go do other stuff, play with your kid, go out with your wife, whatever you like to do, and your brain just grinds away on that. And then you come back to the problem and you go, oh, maybe that's it. And that's kind of what happened to me. I realized that by changing the chord of the elevon relative to the chord of the whole wing, and when the elevon is deflected, I'm changing the entire geometry of the wing. I am changing the washout in the wing, and drastically so. That every time we deflect an elevon or an aileron or an elevator on a flying wing, you're changing the washout of the wing. And depending upon how this elevon is shaped in its planform relative to the planform shape of the wing and the washout that's in the wing, completely changes that washout geometry. That's the aerodynamic washout geometry. And the washout is what keeps the wing stable and prevents spins. So every time this thing moves around, we're changing that essentially aerodynamic washout of the wing. And you change the planform, you go from rectangular to taper or whatever, the geometry changes. And I remember I saw it in my head. All of a sudden, I just saw this picture and I went, could that be it? Is that what's really happening? that I've created a combination of washout, wing taper, and elevon shape that when I went with a tapered elevon and I deflected it up, I was actually ruining the washout effect of the wing. I was ruining the safety margin of stall the inboard portion before you stall the outboard portion. And how that works is this way. When this elevon goes up, the effective angle of attack of this wing is lowered because the chord line, the mean chord line in the wing goes it's the shortest distance from the leading edge to the trailing edge. Well, when the trailing edge is down here and you have the regular airfoil shape, the chord line runs from the leading edge to the trailing edge. But you deflect it up, that chord line now runs from the leading edge up to here on the trailing edge. So the chord line of the wing is changing its angle of attack. That's how the elevons actually generate the pitching moment to pitch up the wing. And if you think about it for a second, depending upon the chord of the wing, the chord of the elevon, where that line is from the leading edge to the elevon, and how those lines are relative to each other changes depending upon the taper of the elevon. If this is, imagine this. Suppose this stays wide here and I took the elevon to 0 here. Well, as it comes up like this, and you have to imagine that this elevon is highly tapered, the change of the angle of attack of the chord out here doesn't change at all because you're coming to a point here, a singularity. And that configuration stays that way. However, the chord line here is going up and down. So you got one here that's fixed. This chord line is fixed at its mechanical washout that's built in the wing. And here you have an aerodynamic washout that's doing this every time you move the elevon. That's if the elevon is tapered this way down to 0. If you taper it the other way, it's wide here and narrow here, you have the reverse effect. This mechanical washout stays the same, aerodynamic washout stays the same, and this guy's going up and down. And that's when it dawned on me, that's washout. That's twist in the wing. So by moving the elevon and given the shape of the elevon, we're actually impacting the aerodynamic washout in the wing. And I had to actually sit down. I was like, wow, I never realized that before. How come that's not written up in books? How come it's not in journals? How come nobody's ever discussed this before? That you're literally warping the wing when you deflect the elevon, depending upon the shape of the elevon, the planform shape. And the amount that you're changing it is directly dependent upon the chord of the wing and the chord of the elevon. And as you change the planform shape of the elevon, that whole geometry changes. And I'm sitting there and go, wow, it's a huge deal. It is a major impact upon the stability and control of a flying wing, and I've never seen it written up anywhere. Like, how come nobody ever saw that before? Are people aware of this? And it's just me, I haven't picked up the right books. And I look around and say, I couldn't find anything on it. It's like, well, maybe I'm wrong. Maybe I just don't understand the geometry. Maybe I got some crazy harebrained idea. I'll go out and test it again. I will take it to an extreme. So I left this wing the way that it is. Straight elevon. Rectangular elevon. On the other wing, you'll see here, if you can see it here, this has a smaller chord at the root end than at the tip. I made it wide at the tip and smaller at the root. So that means as this elevon goes up and down, the amount of washout change, aerodynamic washout at this end of the wing is less than it is out here because of this angle that occurs. So it's kind of like this. It's a weird geometry thing. So as you fly around and deflect the elevon up on this wing, you're actually increasing the washout in the wing and increasing its stability and reducing the likelihood that it'll spin. So here we go, another asymmetrical configuration. We've got the center section in the middle. We go up one elevon on this side, straight. I know it'll spin slightly if provoked. And then we got the tapered one on this side. Take it out and fly it, and what do you know? Spins in one direction, but not the other. It'll spin to this side, but not to this side. Because as the elevon is deflected on this wing, it's washing out the wing more aerodynamically and preventing the spin. And it was stunning to watch. I could not force it to spin to the right, but it would readily spin to the left. It's like, wow, it's real. That geometry aerodynamic phenomena is absolutely 100% true. And that's the gist of what I'm telling you in this video, that the planform shape of the elevon, combined with the washout that's in the wing, the mechanical washout, and the taper of the wing, the three combined together, and you can create a wing. You can create wings that all look the same and they have completely different spin characteristics, and you can actually design it with the proper shape of the elevon to prevent the spins. Now, if you haven't been able to visualize that yet, let me reset here. I'm going to get up the other side of my whiteboard that I already have some stuff drawn on, and I hope some diagrams, some pictures will help you see that a little bit better. And then we're going to come back and talk about how you actually do the design correctly to prevent spins and the parametric numbers that I have to answer that question. So stand by while I get this whiteboard set up again.